and get set up from the current slide. And before we actually get going on real stuff, let's go over announcement type things. Oh, Brian decided to show today. Okay. All right. A few announcements. The volleyball team is, today's the 17th, tomorrow evening at 5, or tomorrow late afternoon at 5, on the Birmingham West campus, our volleyball team will be hosting Southern Union. So if you can get over there to watch them play, I don't know if you realize this, last year we had probably the most successful volleyball season we have ever had here at Lawson State. And I know we lost some key players, but I think we picked up some good ones too. We have, I think, a really good coaching situation now. So that's tomorrow evening. Then Thursday evening they play up at Bevel State in Fayette, Alabama at 6 o'clock. So I don't know if y'all can run up there or not. But, I'll give you the rest of those next time. And some of you know about this already. Is the Scholars Bowl still accepting you folks? Okay. So the Scholars Bowl team is currently recruiting players with knowledge of any subject, including history, literature, science, music, current events, mythology, and mathematics. Okay. We said put mythology and mathematics are close together, but anyway. So see Mr. West, his office is just down the half stairwell here. You know that lab we went to last time, 269, right next to that, between 269 and 259 and 261. I had it wrong on the board. That's his office right there. Okay. The presentation on Darkness and the Light, Life, that was held last night, that's over with now, but the exhibit is still running at the Lawson State College Library on the Birmingham West campus through September 23rd, which I think is next Tuesday. Yeah, next Tuesday. So if you can get over there, take a look. It's really an impressive site. Okay? And then the NASA's Community College Aerospace Scholars Program will be accepting applications through October 16th. So I've got websites and places you can go check it out, find out more about it. There's a nice poster down the hall here, about midway down this long hallway on the left-hand side, featuring some of our former NASA INCAS scholars. Aerospace scholars that have participated in the program, and every one of them looking happy as a clam in that. I think it's a really fun, enjoyable, and useful program. Let me get Ruben here. Has anyone else come in since I called roll? Okay. Now, I did call roll, not like I was supposed to. I was supposed to have printed out something and read to you, and I just haven't been at my computer with the printer on and had an opportunity to do so. But basically it boils down to this. And I think there's probably just two of you, I think three in the class, that this would apply to, so the rest of you just hang on. They said I was only supposed to call roll from the official roster, which means only paid students. And I believe this class has 3 unpaid students to date. So please get your payments caught up, completed, because I think they said that after this week, you're not supposed to come back to class until you complete your payment. With this being a mini-term class, I don't want you missing class. But I put it this way. If you don't pay, you're not going to get a grade. I can't give you a grade because only the people that show up on the grade report are people who have paid. So you can sit in here and enjoy the class and take all the tests and do the labs and learn all this stuff, but you're not going to get a bit of credit for it unless you pay. So complete your payment so you can continue enjoying the class like I know you have been. All right. That's one thing. Another thing is, look how high this stack is getting. Okay? That means I haven't been able to return a single lab or a single test because I've got, let's just go over it quickly. Now, number one, I've received only 4 research papers so far. Okay? 4 out of my best class ever of 26. And we're more than halfway through the term right now. Okay? So this is a mini term. Okay? Lab 1. 1, 2, 3. One person hasn't been here, but he has his lab now. 3 people have turned that in. Test 1, 1 person, 2 people haven't done test 1. Lab 2, 1, 2, 3, 4. One person hasn't been here, so 3 of you that have been here frequently. Test 2, 1, 2, 2 that have been here frequently. And it's not always the same 2 people, folks, okay? One that hasn't. Lab 3, I'm expecting to start getting those anytime now, okay? Diamonds here. Well, we just passed full moon, so I guess it'll be a few more days that you have to watch the moon before it goes down on you. Okay? Test 3, 1, 2, 3, 4 people haven't turned in test 3. Lab 4, 1, 2, 3, 4, 5, 6, 7, 8 haven't turned in lab 4. Test 4, 1, 2, 3, 4, 5, 6 haven't done test 4. Lab 5 completed, I've gotten 4 in. Several of you turned in partials, but remember there's the questions on those. And test 5, 1, 2, 3, 4, 5 people haven't done that. So please, if you're behind in labs and or tests, and you haven't done your research paper, start getting those things in as soon as possible so I can get rid of some of these and not have to haul them around. Yes?
The research paper, you know, that person, what are their life, or would they be?
What? Yeah, you choose. If it's something that has to do with physical science, you choose what you want to write on that. It can be life. It can be how the works they contributed, or a single work they contributed, or something like that. Anything such as that. And Luis is here. Does anyone else come in and says the call roll? So please, folks, get caught up. Okay. It's hard to miss one of these mini-term classes, especially with labs, and not get behind really quickly. So please get caught up. All right, let's talk a little bit about what we're going to be doing today. We're in Chapter 19, Building Earth's Surface, and we're going to be starting today on page 490, and we just have a few more pages, so it's going to take a bit, but not too long to finish the chapter. Okay, we will have the lab that goes with Chapter 19, but it really goes loosely with 19. It actually goes with many of the earlier chapters, too. It's latitude and longitude. It's sort of a fun lab, so it probably won't take you 2 hours to do that. Now, this is also an unusual chapter for this reason. The test bank for this chapter I thought was bizarre. Okay? They were nitpicky questions that had, I wouldn't have wanted to take the test. Okay? So what I did, I redid some of the questions and made a lot of fill in the blanks type thing. There's still maybe a couple of multiple choice, but because I didn't want to figure out your spelling and that kind of stuff, I've decided to make this the one and only take-home test. So when we finish the chapter today, you will do your lab today, and then before you leave, pick up the test for Chapter 19. It's a take-home, and you have 1 week. Please try to get that done. Okay. You're saying way too easy, huh? All right.
Please do more.
Okay. All right. We'll go on and get started in Chapter 20, I'm sure, before the period's over. that's shaping the Earth's surface. And actually, folks, we're moving along faster than I ever would have guessed. But one reason is that we didn't get to go on our field trip. That wiped out almost an entire day. So in a 8-week term, that was pretty major. So we are moving along quite nicely. So there's no reason to rush big time here, but we'll keep going anyway. Any questions on anything we've done so far? All right. We were talking about earthquakes. This was section 19.3, began on page 488. We're just at the beginning of 490 now. We're going to classify earthquakes. And the classification is based on the depth of the focus. Now, someone tell me what the focus is. Or maybe where the focus is.
It's where like waves start.
Yes, that's where the actual earthquake happens. Usually way underground. Earthquakes don't happen at the surface. They happen deep. Okay? You see effects at the surface, but they usually happen quite deep. Okay? So that's the depth. What do we usually talk about rather than the focus of the quake? What's the terminology that they use in the news and stuff like this? How do they place a quake? At the epicenter. And what is the epicenter? Yes, directly above the focus on the surface, that's the epicenter. The focus, though, is where it actually occurred. So the classification of earthquakes here is based on the depth of the focus. I think there's something a little bit bizarre, I think. No, I guess, yeah, this is okay. No, there is something strange about this, and we'll get it corrected. Their graphics person didn't always pay close attention. Okay. Let's start with the shallow focus earthquakes. Down to about 70 kilometers, which is about 420 miles. That seems pretty deep to me. Okay? Down into the earth, 420 miles. Okay? About 70 kilometers. Okay? That is generally into the mantle. Okay? Maybe the upper part of the mantle, but you're in the mantle. That's not a crust earthquake. You don't have many earthquakes in the crust. Okay? So you're in the upper part of the mantle. About 85% of all earthquakes, okay, occur here, and this is because the surface rocks, being cooler, you're not near any of that hot stuff down there, cooler, they're more brittle. So that's what's going to break. They're more brittle. There's more plate friction near the surface. Okay? Down a little bit lower, you get into the semi-liquid, and stuff, so things slide past each other a little better. Near the surface, they do not. So 85% of all earthquakes are shallow focus earthquakes. Then we've got the intermediate focus earthquakes. That's from that 42 miles down to about 180 miles down. Okay? That's pretty deep, okay, directly down. This is in the upper part of the mantle, they say. Still in the upper part of the mantle. Okay? Because guess what? The lower part of the mantle, not part of plate tectonics. What is it where plate tectonics begin? Remember that sphere? A word? A thermosphere, exactly. That's what the plates float on. Below that, the lower part of the mantle, there's no plates, okay? It's all one big chunk of rock. Hollow rock, but still rock. So everything's in the upper part of the mantle. These are in the upper part. These are in the middle upper part, okay, of the mantle, okay? Intermediate focus earthquake. Now here's where the discrepancy comes. Does anyone see it yet? Yeah, we got 50 meters they are missing there. 50 kilometers, which is about 30 miles, okay? We can't be missing 30 miles here. So this is, let me go on and correct it on here. Not that it's a big deal, but this is supposed to be 350. I liked using 300 because it's easier to multiply, but yeah, this is something in excess, probably closer to 200 miles deep, okay? And then the deep focus earthquakes, okay? These go from that about 200 miles deep down to about 420 miles deep. And you're still in the upper mantle, but now you're in the very lowest part of the upper mantle, okay? Only about 3% of all earthquakes come that deep. That's a deep, deep range too, but down there you're getting so hot, you know, it's sort of more plastic. You don't have the rebound, you don't have the other stuff going on. And if you think about it, the movement way down deep is less, whereas up here, because you're further up in the radius, there's going to be more movement, so for the same movement down there. All right. They left off the percentage in the intermediate focus earthquake. What would that be approximately? Second? Okay.
13%.
Yeah, or maybe like 12. Yeah. 3 and 85, 88, 12%. Okay. Yeah, okay. You guys, and you passed my math. No, I'm just wrong. Okay. All right. So about 12% in the upper mantle. Vast majority shallow focus earthquakes. Few in the intermediate focus, and then very few in the deep focus. All right. They do have an example 19, which is sort of a fun one to do. Let's just take a look at that quickly. You're not going to be responsible for doing one like this. But which station is closer to the epicenter if one seismic station in Nevada receives P waves at 4:30:15 a.m., that's 4:30:15 seconds, 4 hours, 30 minutes, 15 seconds, 4:38:15 a.m., and S waves at 4:30:35 a.m., while a different station in California, that's in Nevada, in California, receives P waves at 4:29:59 a.m. and S waves at 4:30:15 a.m. Now that, to me, is almost a dumb question, but I know what they're wanting you to do. Larry? Ethan, sorry. Ethan. Okay. All right. Anyone else coming since I called roll? Okay. Which one? I don't know if any of you have your books. Which would be? The P waves coming in at 4:30:15 a.m., S waves at 4:30:35 a.m., or P waves coming in at 4:29:59 a.m. and S waves at 4:30:15 a.m. Which is closer to the epicenter? What's that? California, for sure. They want you to say the difference between the two and figure out the distance. Hey, the one that gets there quicker, that's the closer. And 4:29 is closer than 4:30. Okay? So that was just sort of a dumb one. Okay? All right. But you're absolutely right. But then to see how much difference you then, in distance, to find the actual distance from it, you do the difference of the two, and that would be 20 seconds for the Nevada quake, 16 seconds for the California station. So you can find out how far you actually are. You do need the difference to know how far. But which is closer? The one that you heard at first. Okay. Now, 19.4, at what time does a seismic station receive S waves if P waves arrive at 11:51:51 and the S waves arrive 75 seconds later? That's just an addition problem. How many minutes is 75 seconds? How many minutes is 75 seconds? A minute and 15 seconds. What's that?
1 minute, 15 seconds.
1 minute and 15 seconds. Add that to 11:51:51. Well, 15 to 51, and 9 of those 15 seconds that are gone to 52 minutes, and then the other 6 seconds. So that would have been at 06, and then carry a minute, then you add a minute, that would be 53:06. That's just adding time. Has really nothing to do with earthquakes, except they're measuring the difference. Some of these questions are meaningful, and some of them are make work, it seems like. All right, so let's move on from there. How do we measure earthquake strength? There have been several methods that dealt with it to some extent. Here's what they've looked at in the past. They've looked at the effects of the earthquake and tried to measure the strength from that. Well, the effects would be structural damages to building, fires, landslides, displacement of land surface. Remember that field with the roads? I don't remember what was planted, how the roads were shifted. That's a measure of earthquake movement anyway, displacement of land surfaces. Or if you happen to be near the water, the earthquake was over one of those subduction zones in the water, you could easily have a pretty major tsunami. And that would be an indicator of how strong the earthquake was. But depends on where you were and what that was. One of the strongest earthquakes ever to hit, I believe it's still one of the strongest, was in Alaska. But this was some portion of Alaska that was very sparsely populated. This was many years ago, too, before it was populated as much as it is now. And it was such a strong earthquake, the tsunami from that earthquake wreaked havoc on Hawaii. And Alaska and Hawaii are quite a distance from each other, and that tsunami carried that far and wiped out the northeastern shore of some of the islands of Hawaii. So, yeah, those are ways that you could measure. But you see, remember I talked about the earthquake in Haiti, followed about a month or two later by one in Chile. Haiti did way more damage to buildings because their buildings weren't built as strong. So you can't really tell always by looking at things like this. The fires, San Francisco, if I'm not mistaken, the big one in San Francisco around the turn of the 20th century, way back 1906 or something, whenever that one was, more buildings were destroyed by fire because most of the buildings were made of wood, So the fires were, and they had the gas lines that were underneath the roads and stuff, they were split, and then when the fires lit, we were just blowing up gas all over the place. So not a good measure of how strong this quake was, okay? But it certainly measured how much damage there was. Back on these kinds of things, they came up with a scale. A guy named Mercalli, who you can write on if you like, came up with the Mercalli scale. Sounds like a good Italian name to me. I don't know that it is, but I believe he probably was. And not too unreasonable either that it would be Mercalli. Think about, this is another issue here. Let's see. 1 think about where Italy is. The boot that sticks down into the Mediterranean here. Well, let's think about plates. Is there a plate nearby? Well, certainly Europe is on the Eurasian plate. But just below that is the African plate. And hey, those two plates may be colliding, grinding. And Italy has had its fair number of earthquakes. Anyone ever heard of Vesuvius? Yeah, that was a pretty major volcanic eruption, wiped out an entire city, and later people had forgotten the city was even there until I think it was a farmer who was digging in his field and found something really bizarre and reported it. They started digging around, found an entire city covered with the ash down there, Pompeii. Okay? Wherever there's volcanoes, there's a good chance there's earthquakes. My wife and I have taken several of her nieces and nephews on trips overseas when they graduated from college. And just about every one of them wanted to go to Rome. Okay, so we've been to Rome a few times, and they'll tell about this was damage to some earthquake, blah, 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 blah. And, so there's lots of, Rome has seen, or Italy has seen its fair share of earthquakes. This is Zari, right? All right. Is anyone else come in while I wasn't paying attention? Okay. So, not at all surprising, a guy named Mercalli may have come up with a way to measure earthquakes. These were relative intensities, relative to other quakes they may have seen in the past or somewhere. So this was the Mercalli scale. The level 1 is one that you can't really feel, okay? Very low intensity. Up to 12, which is total destruction, and you remember the surface waves, not S waves, but the surface waves, visible surface waves. You could really tell major destruction there. So that's relative intensity from not feeling them up to total destruction. But again, something out in the wilds of Alaska, where would you do that? No one was around to feel it, so that's not a very good thing. And it's one of the biggest ones ever done by the tidal wave. So it's sort of not maybe the best way to do that. All right, now, they have this little blurb here. I can't remember. I don't think they're going to do the same one later. I think that's a tornado one they do in 2 places. Very, very similar. And it seems out of place here, but since they've shown it here, let's go and talk about it. Earthquake safety rules from the National Oceanic and Atmospheric Administration. By the way, if you ever hear people talk about NOAA, that's not a person. That's National Oceanic and Space and Atmospheric Administration. In fact, it was a fairly recent time that NOAA was in the headlines, especially here in Alabama. Any of you know what I'm talking about? Didn't you know we had a 95% chance of getting hit by Hurricane Dorian? No, we didn't. But someone listed had. And NOAA came out, or the National Weather Service came out and said, no, there's no chance Alabama's going to get anything. But we didn't want to risk it, so we evacuated to Georgia. No. That's right where it would have been coming from. Anyway, NOAA got in on the political fallout of that. I think the head of NOAA was threatened with losing his job if he didn't come out. That's politics. Let's not get into that. Okay, too much. All right, during the shaking, it says don't panic. That's sort of a hard thing not to do, but guess what? It's not going to do you any good, okay? So try to keep your head about you and try to think of what you can do that's constructive. So don't panic. If you're indoors, stay in there, okay? Things can fall on you outside just as well as inside. Seek protection under table, desk, doorway, somewhere where the strength is there. Stay away from glass, because when there's shaking going on, things can get distorted and glass can get splintered and fly across the room, okay? Don't use matches, candles, or any open flame. If you got a fire going, put it out, because there's a good chance, as happened in San Francisco, gas lines can be broken easily with earthquakes. Very much activity. So no open flame. Just because the lights go out, don't light a match to see where things are. If you don't have a flashlight, all of you have cell phones, use your cell phone. Okay? Never mind. Okay? If you're outside, get away from buildings. That's why they don't want you going out if you're inside, because leaving a building, is this a brick building? Second?
I think so.
No, it's a brick facade building. That brick is not doing anything structurally to the building, it's just a facade, meaning a shell. So it can easily, and bricks start falling and flying off. It's more of a concrete block building, okay, which is not the best in earthquakes either. But anyway, if you're outside, move away from buildings, away from power lines, stay in the open. Far better than underneath something. For instance, if you're on the highway, don't say, oh, there's an overpass, let me get under it and be protected. No, okay, because overpasses can fall. Talk with the people in Los Angeles who went through the quake there. Overpasses collapsed on top of cars underneath, not doing good things to the cars. Okay, stay away, stay out in the open. Don't run through or near buildings. Okay, now this is not an earthquake, but my younger brother, it was my summer after my sophomore year of college, freshman. Let me think. Yeah, after my freshman year of college. I was in Navy ROTC, and I was sent on a 6-week or so midshipman cruise, is what we call it. So I was away, first time I've been away from home for that long, certainly all by myself, not around any family whatsoever and stuff. I was really looking forward to coming back to Virginia, because my mom had several brothers and sisters living in the Virginia area, and so they were going to come up and see her siblings, and it was going to be a great time. Well, my older brother was going on he was finishing his junior year, and he was going on his first class midshipman cruise, and he was also leaving out of, he was flying, he was being flown over to Spain. I didn't know it at the time, but he was flying to pick up the ship in the group that we went over with, and so anyway, that was different. Well, he and my younger brother had gotten into some sort of spat, and my younger brother didn't want to go take him to the airport or wherever it was. So he had arranged to spend the night with a friend. He had gone into town, spend the night with a friend. Well, this is a small rural town. Not much activity, nothing of any interest going on there. And they heard the fire trucks, local volunteer fire department. Let's go see what's happening. That was the most excitement for Georgia has to offer. So they went, and sure enough, there was a fire in a sort of a poorer part of town where the houses were really close together and built out of materials that were very flammable. So I couldn't believe my younger brother cared enough to say, let's see if we can help these people. And he did. He and his friend started helping people move their belongings out of the houses that were close, so if the house did catch fire, the belongings weren't going to be destroyed. So they had been moving stuff to safety. The fire department put the fire out before it got to them. So now they were helping move the stuff back inside. And the houses were close together, and he was passing between a house that had burned and the house that hadn't burned. You know, and someone from the local volunteer fire department thought, well, won't it be neat to spray the chimney and watch the steam come off of it with the high-powered, high-pressure water hose? And he did, and the chimney fell on my brother. Okay, and there were certain places where the hot side of the bricks were against his skin, and he had third-degree burns, and many places where he had first and second-degree burns. And he was knocked out too. And my parents were out of town. They took him to the emergency room, but they wouldn't do a thing for him until they got parental consent. And my parents were out of town. And this was before the days of cell phones, okay? So there was no way to get in touch with my parents. They were taking my older brother to his flight, and on their way back, and when they did come back, they got the word, and it was a mess. Well, then, from then on, my mom was taking care of my younger brother, working on the third-degree burns, so they weren't able to come up to meet the ship when it came in. Why am I on this long story? Okay. The point is, don't get near buildings. Okay? Because unstable things can happen. And chimneys could fall, walls could fall, bricks could fall off the sides. You don't want to be near a building when there's something as unstable as fires or earthquakes, have happened. So don't run through or near buildings. Anything could happen. If you're in a moving car, bring it to a stop as quickly as possible, but stay in it. The car will provide some moderation of the shaking. It's got a suspension system, okay? But not under an overpass, okay? Don't park there, okay? This car springs will absorb some of the shaking. It will offer some protection. But don't get under something in a car. Get under a table or something if you're inside a building, but don't get under something outside that could shake. Now, after the shaking, check but do not turn on any utilities. If you smell gas, open windows, get out of the building, okay? Open windows to minimize the risk, but then get out of the building. Shut off the main valve if you know where it is. Leave the building. Report the leak immediately to the utility. Don't re-enter the building until it has been checked out. If water mains are damaged, shut off the main valve if you know where that is. If electrical wiring is shorting out, arcing and sparking somewhere, if you know where the main switch is, close the switch. Otherwise, it could ignite gas that's leaking or something like that. So do as much as you can. That's why they say don't panic, think. Think of positive, constructive things you can do. Turn on radio or television if you have power for emergency bulletins. Stay off the telephone except to report emergencies like gas leaks and things like that. Okay? No, you're in here. Yeah, got it. Latricia. Is it? Yeah, Latricia. Just had. Why am I holding the glasses rather than wearing them? I don't know. Okay. Now, so I can see y'all. Oh, and here's Maya. This time I'll put them on. Maybe I can find it sooner. All right. Stay off the phone except to report emergencies. If and when there are things like earthquakes, phone lines can be disconnected, so there may be, as antiquated as the phone company's infrastructure is, they do have relays and stuff like this to get around it, but the more traffic you've got going in it, the slower and the worse the system becomes. Cell towers can topple, so you don't want to be on the cell phone because, again, you could have limited range and stuff like this in cell phones. So stay off the phone except to report emergencies. Stay out of severely damaged buildings that could collapse with aftershocks, because just about every major earthquake is going to have aftershocks. Things don't just settle out immediately. There's usually aftershocks. Sometimes the aftershocks are almost as bad as the original quake, and since things have been damaged on the first one, it can be even worse with the aftershocks, even though they may not be quite as strong. Okay? And do not go. And this held for the tornado damage that we had April, what was that, 2011, and actually earlier ones. People just thought, oh, boy, I heard they really got dumped on. Let's go see. You know, no, don't go see. Most of the time, in fact, I heard in that 2011 episode, there were people here at the school who couldn't get to the neighborhoods they lived in, you know, because there was so much traffic of people trying to go see. I think Pleasant Road got hit pretty badly, and Pleasant Road was hard getting in and out of Pleasant Road because roads were damaged, power lines were down, trees were down, and then there were people trying to, let's go see how, I already got, let's go. No, stay off the roads. Okay, don't go sightseeing. It will only hamper efforts for emergency personnel. So same type of practical, common sense things that you do for tornadoes, you do pretty much the same thing here. Stay out of buildings that have been damaged, that kind of stuff. Okay. Again, that sort of was stuck in there at a weird place. But let's get back to measuring earthquake strength. Okay? Nowadays, we use another scale called the Richter scale. This guy was Charles Richter, the potential paper topic here. Guess where he was from? Good old U.S. of A. What part of U.S. of A? California. Hey, they know earthquakes, okay? He came up with, based on swings in a seismograph, recordings. And those are things we've seen before in the book, and I think maybe even on a slide that shows the swings of things. So here's what a seismograph is. Oh no, this is the ranges. It's a log scale. Does anyone know what I mean by a log scale? In a log scale, you go up by orders of magnitude. Okay? Let's say if you were evaluating the damage of something and it was 2,000 whatever units of energy or whatever, that would be 2 times 10 to the third power. Okay? Well, something else might be 20,000. That would be 2 times 10 to the fourth power. A log scale measures the power. Okay? So the difference between a 2 and a 3 is a difference of 10 times, because every power of 10 bumps it up one more thing. So 0 to 2 is the smallest detectable earthquake. You're not going to feel it. The seismograph will record that. You'll just see a little bit of motion, just a tiny amount of motion. Probably takes an expert reader to say, oh, that was an earthquake, you know, very, very weak, but it was. 2 to 3, detected and measured, but not generally felt. You still don't feel those, but they can easily detect and measure that. 3 to 4, felt as a small earthquake, but no damage occurs. Now, a lot also depends on how far you are from the quake, right? Where do most of our earthquakes occur in the U.S.? The West Coast, right? The Ring of Fire, okay? Around the Pacific Basin, okay? But there have been quakes in other parts of the U.S. Can anyone name one? Second, New Madrid Fault, right? That was a pretty major quake. It was way before my time, but they said, I've heard that the Mississippi River actually flowed upstream for a while. It was that major quake. Okay? Well, there was one within the last decade that happened near Washington, D.C., actually somewhere out in Virginia or somewhere, but it was felt in D.C. because the Washington Monument cracked. Okay? And they would not allow people into it for, it seemed like a couple of years. While they measured, made sure they detected all the damage, got it all repaired. So there was a while no one went in the Washington Monument. Now the reason I'm saying that, I grew up in Georgia, okay, south of Augusta, Georgia, over here, and the farm's still there, and my wife and I own about a quarter of it, because it was split among the 4 kids. And we had just recently built the 2-bedroom bungalows, so when we went over to the farm to take care of farm business, we had a place to stay. So we had this house there, and Karen's sister had given her a sign that said farm, a little metal thing that you hung it on the wall. And we came home, or went to Georgia the next time, it was on the floor. And we said, why would someone take this off the wall and put it on the floor? And we just mentioned it to my sister-in-law. She said, oh, that must have been the earthquake. Well, I had heard there was an earthquake in D.C. that had damaged the Washington Monument. I didn't know it was felt in Georgia. She said, yeah, things just sort of shook a little bit there. So that would have been like this. Felt as a small earthquake, but no damage occurring, except farm signs falling off the wall. No damage. That was it. 4 to 5 minor earthquake with local damage. That would have been what they felt in D.C. Okay? Again, it wasn't a major earthquake, but it did do some damage. 6 to 7 strong earthquake with destruction. That's probably describes Haiti and maybe Chile. Those two made fairly strong quakes there. 7 to 8 major earthquakes, extensive damage and destruction. Okay? Extensive. And those, I'm just going to make a guess on this one. Remember, it was near Christmas. The Haiti was too. I think it was the day after Christmas. But it was near Christmas a few years ago that it happened off Indonesia. And the tidal wave went all the way across the Indian Ocean and wiped out, killed a lot of people on the beach in India. We have friends from what used to be called Madras, it's now Chennai, that's near the water, and they had relatives, cousins or something that were down at the beach that day. I think all of them survived, but many people did not. The tidal wave was that major. I think that was probably one of these major earthquake extensive damage. A few years after that, and you want to hear of Fukushima? That's, again, the ring of fire here. The subducted ocean plate underneath the island arc of Japan. There was an earthquake there, just off the coast, and just at the coast was a nuclear power plant, Fukushima. And Fukushima had major damage. Well, what made it major was the power went off. And when the power went off, they couldn't cool the reactor. When they couldn't cool the reactor melted down. Japan is now refurbished. Or if they're going to depend as much on nuclear power, I think they're going back to more fossil fuels. Japan. But that was pretty major. Okay?
Did a lot of people get killed from that?
Not as many as you would think. It was and I don't know, count still may be going up because of radiation, but it wasn't as major a death total. It was kind of, it wasn't, I think it was on, if I'm not mistaken, an island called Honshu, the one that, Honshu. Same island that Tokyo is on, but Tokyo is here and it's up in this portion, I think. And so it wasn't that highly populated an area. I usually think that Japan is completely filled, but there are some areas of Japan that aren't. And that's where they tend to build nuclear power plants, is not in population centers. So but it had to be a fairly major earthquake to cause that. And then the 8 to 9s, great earthquakes with total destruction. That's probably what, I'm pretty sure that was the one they had in Alaska, somewhere down here in Alaska, that the tidal wave went all the way down to the Hawaiian Islands. I mean, that was a major, that was a 9. I think may have been the highest that's been recorded at that time. It may be they've had a few higher now. Not many people were killed because it was a very, very remote area. Okay. So that's, before we turn the page, I've already said this before, myths, mistakes, and misunderstanding. Do earthquakes swallow people? Only in the movies, okay? They don't really happen. It's not the earth opens up and people and cars fall in the hole. It doesn't happen that way. The quaking, the shaking is what happens. Then things fall on people, but people don't fall in. Top of page 492, that was that, okay? You'll see the same blurb there that you see here, okay? And then the bottom of page 492, you see this, okay? And this is the Richter magnitudes, all right? Now, some things to remember about the Richter scale, okay? Again, so developed by Charles Richter, a seismologist at the California Institute of Technology, Caltech, in the early 1930s. And what it's actually measuring is the severity of the ground shaking vibrations, which also relates very closely to the energy expended in those vibrations. Now, rule of thumb, when you go up 1 digit here, 10 times the shaking, okay? This is in your text. The amount of ground movement is increased by a factor of 10, but the amount of energy released is a factor of 30 for a 1-digit increase. So a 5.2 quake, moderate earthquake, 6.2, 10 times the amount of ground movement, 30 times the amount of energy expended, released, damage done, in other words. So when you get up to a 9, goodness gracious, that's an enormous amount. 5.2 to 9.2 would be 4 zeros after a 1 for ground movement. That would be 10,000 times more powerful, more ground movement. 30 times that, 3 to the 4th power is 81, 810,000 times the amount of energy. That's a lot of difference. Okay. And that leads to example 19.5. And again, you don't need to know that, but compare the energy released by an earthquake of 7.2 magnitude to an earthquake of magnitude 5.2. 5.2 moderate, 7.2 major. What's the ground movement difference there? Now they're asking energy, but what's the ground movement difference? Going up by 2 is how many zeros to put after your 1? 100 times more ground movement. But what would be the energy? 30 times 30. 900 times the amount of energy released. Okay? So, ground movement, 1 with that many zeros, what your difference in magnitude is. That measures how many powers of 10, and if it's energy, it's powers of 30. 30 times 30, a difference of 2 on the scale. All right, example 19.6. Compare the amount of movement of the ground. Oh, I already gave this one away. Surface amplitude associated with the 2 earthquakes in 19.2. Second earthquake had 100 times the ground motion. Okay. Now, There it is. This is the place. What you couldn't read a couple of slides ago, here it's printed bigger. Okay, same information. It's the top of page 492. I was thinking it was going to be in the next couple of chapters when we did tornadoes, but no, this is where they did it. They put it in fine print. On the other, they put it in big print here. But we've gone over this already, so I won't spend any more time on it. Now, notice in your text on page 493, there is several paragraphs on tsunami. And tsunami is a Japanese term used to describe the very large ocean waves that can be generated by an earthquake. That's what the Japanese call it, tsunami. That's why it's a rather unusual word. It's not shown on the slides here because they're going to wait and do the slides on that in chapter 24 when they talk about Earth's waters. So that's one place that the changes occur. But please read the book because just to get an idea of what they're talking about here. They rearranged the book between the making of the slides and the edition we're in now. Okay. The thing about tsunamis that I find almost unbelievable is that most common ocean waves are produced by winds, travel at speeds of 90 kilometers per hour. That's about 55 miles per hour. It's like a car going down, not the interstate, but any major highway. 55 miles per hour. That's most waves, wind-driven waves. They produce a wave height of about 2 to 10 feet. 10 feet is a major storm that's produced a wind-driven wave up to 10 feet. Most of them more like 2 feet, especially when they break on the shore. A tsunami, on the other hand, is produced by some strong disturbance on the seafloor, travel at speeds of 725 kilometers per hour, which is 450 miles per hour, as compared to 55 miles an hour. 55 miles per hour is pretty fast. I can't outrun that. 450 miles per hour, hey, I can't think of many things that can outrun that. Jet planes, but they're not in the water. No ship, no boat, nothing will do that. Produces a wave height of over 8 meters. That's about 25 feet, as opposed to 10 feet for the strong storm wave. 2 feet normal. A major storm might produce a 10-foot wave. Tsunami, 25 feet when it breaks on the shore. Now, this next one, a very long wavelength, about 120 miles between the peaks, the crests, okay? But when they're traveling at 450 miles per hour, that means it takes a fairly short time for that next one to come and hit you too. So don't mess around with tsunamis. Now, I think I've told you before, this chapter hits both of them. Internationally speaking, the two, in my mind, best things that science has put together internationally has been seismology, in other words, the seismograph system, that they have the stations set up everywhere, they communicate with all. It's a great system, and people abide by it. Even countries that don't get along at all, they'll still contribute to that. Scientists sort of overcome politics a lot more than many others do, okay? So seismology is one, tsunami system is the other. The tsunami system, now this is mostly countries that border oceans or big things of water. They have the tsunami system set up, and they communicate very, very well as well, okay? Now, those were general numbers that I just did. The long wavelength of a tsunami, 120 miles, as opposed to a length of an ordinary wind-generated wave, about 1,300 feet. That would be, 430 yards. That's pretty major, but nothing like 120 miles, okay? Because of its great wavelength, the tsunami does not just break on shore, then withdraw. Depending on the seafloor topography, the water from a tsunami may continue to rise for 5 to 10 minutes, flooding coastal regions before the wave withdraws. So it's a long wavelength, and it's not just washing up and going back. It can be there for quite a while. 5 to 10 minutes can do a lot of water damage. Now, a gently sloping seafloor and a funnel-shaped bay can force tsunamis to even greater heights as they break on the shore and are funneled in canyons and fjords. The current record height established in 1958, when a tsunami reached 524 meters, that's 1,720 feet high. That was in Lituyo Bay near the Gulf of Alaska. I think that's the one from that major earthquake they had there. 1,720 feet. I can't even picture that. I mean, that's mountains. No, I'm sorry. Okay. Waves of such great... What's that?
That tall.
That tall, yeah. Waves of such great height and long wavelength can be very destructive. Okay? So, you'll see that later in a later chapter. It's not on the slide set here. I'll remind you when you see it. All right. New topic, 19.4, origin of mountains. Okay? Now, we've already hit some of the terminology for it, but we haven't put it together with earth forms. So now we're going to do that. Mountains. What is a mountain? This is completely off subject, but it was a pretty interesting movie based on reality. I can't remember which war it was after World War I or World War II. Sometime or another, in Great Britain, they decided to go and do surveys of their lands and stuff like this and update their maps, cartography. And there's a place, I think, in Wales, and they were very proud of their mountain. I don't remember what the name of the mountain was. But when the survey crew came out, it would be a power geological survey, they came out and measured the mountain, and it had eroded enough, or there had been enough errors in the earlier measurement that it was just short of being classified a mountain, so it was going to be reclassified a hill. And the people in the town just were upset at this, because that had been their mountain, and now it's just going to be called a hill. And they didn't like it. So what they did, they started hauling rocks and stuff up the hill, up the mountain, building up the peak again until they reached it. Well, it wasn't that many feet that they had to go, but it was significant, especially since they had to form the rocks and make it. The name of the movie was The Man Who Went Up a Hill and Came Down a Mountain. Okay, that was the name of it. Starring, goodness gracious, funny guy who was in Pride and Prejudice, and Hugh Grant. Hugh Grant played a good role in that movie. Okay. The only reason I really remember the title, it makes a great charades title, The Man Who Went Up with the Other. Okay. But anyway, y'all don't even know what charades are. Okay. What a mountain is an elevated part of the Earth's crust rising abruptly above the surrounding surface. Okay? There can be some very high plateaus, but they're not mountains because they don't rise abruptly up above the surrounding surface. They're very gradual in their ascent. Okay? The Tibetan Plateau would be a higher elevation than most mountains in the U.S. But it's not a mountain. It's a plateau because it's a gradual rise, not an abrupt rise. Okay? It's created, and here's where the terms came in. Remember when we talked about folding and faulting? So there's these two types of mountains, folded and faulted, of the crust. Okay? Now remember what folding is? Folding is usually happens somewhere way, way deep, and when the rock material was still fairly plastic and was hot, and it folded, and then later pressures moved it up, and then that became the mountain because it rises abruptly. Other things eroded away. But faulting is when there's a break. Faulting and the joints are breaks. Okay? Faulting is when there's a displacement. And that is called the fault block mountain. Okay? So mountains are quite often folded or fault block mountains. And then there's one more, volcanic mountains. Okay? And there's three classes of volcanic mountains too, but we'll get to that later. Let's look first at the folded and faulted mountains. Now, one folded mountain would be a domed mountain. And again, I don't know if this classifies or not, but to me, that's what Stone Mountain is in Georgia. Okay? It rises abruptly around sort of flat surrounding, and it just came, and it was a dome type thing originally. It just is there. Okay? A broad arching fold. What do we call a arching fold? Oh, how soon we forget. Starts with A, as opposed to a trough. Starts with S. Anticline. Syncline. All right, long time ago. Okay, at least a week. Okay, began as a broad arching fold and continued building from there. Overlying sedimentary rocks that were there, that's what got folded, they weather away. Now we're going to talk about that in the next chapter. Weathering away, leaving the more resisting granite peaks like Stone Mountain, that's granite. So other things erode away, the sedimentary rocks that break and fracture fall away, and leaving the more resistant granite peaks. Much of, and there's a good picture in your book, I don't think they show it on the slide, a aerial shot of the Appalachians. Okay? I'll hold it up here. If you got a book, you can look at it yourself. The folded structure of the Appalachian Mountains revealed by weathering and erosion, that you can see where that is obvious in the Skylab photograph of the Virginia, Tennessee, Kentucky boundary. The clouds over the Blue Ridge Mountains, and sort of give you an idea where they got the name, those are the Blue Ridge, which are part of the Appalachians. But you can almost see the folds, how they built there. Now, since we're talking about the Appalachians, they are perhaps one of the oldest mountain ranges on the planet. Okay? But they're not growing. They're eroding away, weathering away. They're actually going down. And if you go to the Appalachians, you'll see most of the mountains are rounded on top. You don't see very many sharp peaks. The peaks have all been weathered away. They're rounded. That indicates they're being worn down. Okay? Even some of those granite peaks. Some of those may have a little bit of sharpness to them just because they resist weathering like crazy. But those are your domed or your folded mountains. Now, remember we were talking about Italy? what's just north of Italy and Switzerland, or in Switzerland, then the Alps. The Alps are much younger mountains. They're still growing because of this plate movement. There must be some sort of movement together, and there's folding going on. Well, there's all sorts of activity there. Just like the Appalachians, where the Eurasian plate hits the India-Australian plate, and that's where the Himalayas are there. Even our Rocky Mountains are growing. Our Appalachians are shrinking, decreasing in height. At one time, the Appalachians may have been some of the taller mountains on the planet. We don't know. We weren't around, but that's the prognostication. But those were mostly folded mountains. Okay, this is kind of illustrating what they're talking about here. This is the dome happening. You don't know why it's happening. Somewhere down here, there must be a weakness somewhere down there, and pressure is pushing things upward. Okay? Now, as it pushes upward, this stuff gets stretched and cracks and erodes, and you wind up with this left over, and that hard stuff that was in the middle here, that then forms your dome mountain. That could be, on a much larger scale, Stone Mountain here with everything else washed away over there. Okay? That's why they call it a dome mountain. It started as a dome in the Earth's crust, and then other things wore away. I guess those are supposed to be cracks and crevices, and then you wind up with a mountain here. Now this is a huge scale. This comes up well above the surrounding terrain. Okay. Now, next are the fault block mountains. The faults, remember, when faults happen, what's the underside of a fault? Foot wall. The upper side, hanging wall, okay? And when it's a tensional force, the hanging wall slides down, so you have a block rising sharply. That would be the foot wall hanging up there. But when it's a compressional stress, then the hanging wall is pushed up, and that is what rises sharply above the surrounding. Okay? But all the while, and this is next chapter, weathering is occurring that wears it down. So this is a really idealistic type thing. Remember, they had the Gravens and the horse, and I never remember which is which, but that doesn't matter here. Which would this wall be? That's the foot wall. That's the hanging wall. It fell down. So what kind of stresses were these? Tensional stresses. You see, again, here's the foot wall. There's the hanging wall. It slid down. Foot wall, hanging wall, it slid down. Foot wall, hanging wall, it slid down. Tensional stresses, and so these form your mountains then. Fault block mountains. But over time, especially where the breaks occurred here, and these lots of surface area here, this gets worn away by wind, by rain, things blowing against it, and it wears down, filling in the valleys with sediments, which will form what kind of rock later? Sedimentary rock, okay? And that's right next to maybe the hard granite rock that was left here. So now this is what, even though there weren't fault block mountains, this is what's happening to the Appalachians now. They're wearing down. But they were folded mountains to begin with, not fault block mountains. Does that make sense? Okay. So you look at the mountains you happen to see, and if they're really jagged, they're probably fairly new mountains. They haven't been weathered very long. If they're really rounded, whatever kind of mountains they were, folded or faulted, they're wearing down. They're probably decreasing in height. Okay. And then we have our volcanic mountains. Okay? And these are usually your picture-perfect mountains, okay? The ones people like to take pictures of. It can be just a hill. We'll see some in Hawaii that are basically just hills, or mountains formed by extrusions of lava. But when it comes near the surface, what does it become? Oh, I'm sorry. What was it before it became lava? Magma. Underneath it was magma. When it reaches the surface, it becomes lava. Or rock fragments, okay? Because sometimes when those volcanoes blow, they're blowing out chunks of rock too. Rock fragments or molten material, lava, which was magma, from magma below. Okay? They give three things about the structure, but don't illustrate them. One is the vent, other is the crater, and the other is the lava flow. And I have not found a picture that describes those very well. The closest I would get would probably be figure 1921, the upper part of that. And let's see if, I don't think they show it here. No, they show here, I'm pretty sure that's Mount St. Helens. Let me see. Or, no, that's Mount St. Helens. Several years after the 1980 explosive eruption. And I think earlier we were saying that was the most destructive volcanic explosion in U.S. history. And remember, we talked about how many people were killed, and acres and miles of roads and rail lines and stuff were destroyed. The vent, if my understanding is right, would be where the first cracks or whatever occur that stuff starts coming out of. I think that's what the vent. The crater, of course, is the big hole left over after it blows. Okay? The lava flow, you can see that's where the lava has formed down the sides of the mountain. That's the lava flow. Okay? Now that's the best I can do. They just don't illustrate the vents. The crater is pretty obvious and the lava flow is pretty obvious. They don't do a good job of telling you what the vent is. But I believe that's the place. Let's see if they have that. I don't think they do. Let me see. Yeah, there it is. That's the one I was looking for. These would be what I would consider the vents. Okay? And then if there is a crater form, that would be that. Now this is, I think, Mauna Loa or Mauna Kea. Mauna Loa in Hawaii. Okay? And you can see here was one, here was one. You know, there were several places where it vented and then sealed over and vented somewhere else later. I think that's what the vents are. And then what's left over are little craters. Okay. Jordan, right? All right. Finally building up a decent class size. Now, before I should have done this before we got to this. I just didn't pay attention to it. Here are the Tetons. Have y'all heard of Tetons? In Wyoming. This area around down here is sort of it's kind of like a bowl. It's got mountains on one side, really tall mountains, that's the Tetons, and then there's other mountains on the other side. So it looks like a hole in the middle of the mountains. And you know what they call that hole in Wyoming? Jackson Hole. You'll hear people talk about Jackson Hole, Wyoming. That's where a lot of very rich people build mountain getaways or whatever. We've been there a couple times just because it's near Yellowstone, and it's cheaper than Yellowstone, but it's still fairly expensive. But cheapest you can get and still be close to it. That is the Grand Teton, I think, in the middle there. That's what you call, let me back up, a fault-block mountain. This is the figure opposite that one in your text. figure 1918, the Teton Mountains of Wyoming are fault block mountains. Notice how jagged they are. There's been some wearing away with time, but they are very peaked and pointed mountains. Very, very jagged. Fairly recent mountains, and are still growing. Okay? And they're right out in the middle. I mean, Wyoming's a long way from the shore, but the pressures elsewhere are building up these mountains. Okay. Let's get back to the volcanic mountains. Okay. Here are the types of volcanic mountains. Okay? We'll go each of these separately in a minute, but shield volcanoes. These are constructed of solidified lava flows. Not huge chunks of rock most of the time, solidified lava flows. These are broad, gently sloping cones like we saw with Mauna Loa. I mean, hardly a mountain at all. These are almost just hills, okay? But those are shield volcanoes. Then you have the cinder cone volcano. These are constructed mostly of rock fragments, which are your cinders. These are when the volcano blows and blows more rock up, then it blows up lava. This is almost totally lava. This is almost totally rock fragments. These are steeper but smaller than the shield volcanoes. Shield volcanoes are very broad but very gentle slope. You could look like to me on Mauna Loa, you could probably walk up there fairly easily. You're not climbing the mountain, you're just walking up the slope. These are much steeper, but they're smaller. And I don't think the slideshow has them, but in your text, on figure 1922, and the trouble is, you don't have anything to gauge how big or small this is because it's just there. Sunset Crater, a cinder cone volcano near Flagstaff, Arizona, and you can see it's one of these almost perfectly formed little volcanoes. Not really all that tall though, okay? So that's your cinder cone. And then you have your granddaddies. These are composite volcanoes, alternating layers of cinders, ash, lava flows, and volcanic mud. I mean, it just has everything. And these things sometimes get very, very tall, majestic mountains. Fujiyama in Japan, Mount Rainier off Seattle. On what few clear days you have in Seattle, you can see Mount Rainier. Mount Shasta. Mount St. Helens was probably a composite volcano. The big, massive, picture-perfect volcanoes. The picture on figure 1923 shows Mount Shasta. It doesn't do it justice because you're taking it from way high in the air. Beautiful picture even then, but you just don't get the scale of it. When you realize that snow is the white stuff and going down, you're probably in summertime around there, you get an idea of how tall this thing really is. But that picture doesn't do it justice. Okay, and there was again Mauna Loa and some of the illustrations. This is your shield volcano. Mostly lava flow, gently rolling. Okay? And this is another picture of Shasta here. You can get a better idea of the majesty of that mountain. And here's a few things here, and again, they don't show what they call a vent, and this irritates me. But the crater is certainly this thing up top, but I think these things like here are also called vents, the little sideshows that you have there. The deposits, okay, lava flows, but also volcanic mud, ash, cinders, whatever you have around there. Shasta is a composite volcano. Okay. Now, I can't figure out where its crater is unless it's right there. It's sort of like Mount St. Helens. It may have, on its last eruption, which is who knows when, not in recorded history that we know of, may have blown the whole side or top of the mountain off. So, because that sure doesn't look like much of a crater up there. That looks like the most likely crater there. Now, I know I've done some talking about Yellowstone, and if I haven't said enough about it, please ask me, I'll say more. If you have a bucket list, something that you want to do sometime during your life, please add going to Yellowstone National Park. That is the most incredible collection of volcanic-related artifacts that you'll find anywhere on the planet. Russia has a few areas that may come maybe second or third, and they just don't even compare to Yellowstone. Yellowstone has so much variation there. And the reason, and when you drive into Yellowstone, especially from the Wyoming side, you'll pass this huge lake, Lake Yellowstone. And that huge lake that you see there is just part of the crater of the volcano that blew its top sometime in the past. Massive, massive volcano. I mean, that huge lake is just part of this crater. And then you'll go up other places as you're traveling around. And Yellowstone's a huge park. You drive literally hours going from one part to the other part, and you see so much activity there. But you'll be passing over, and this is part of the caldera. This is part of the other part of that crater. That's the low part, which filled with water. This is the upper part here. And you've driven miles since you went from there, so that crater is huge. Okay, so please, if you can, visit Yellowstone sometime in your life. It's worth it. Okay. Now, there are other features, and these are all mostly caused by magma. Okay, what's magma? Magma, molten rock. Magma, molten, melted, it's liquid rock. Okay? Most of that magma remains underground. Okay? Now, some of it that's been forcing up somewhere may be what's causing those dome mountains, the folded mountains we were talking about. The magma somewhere way under there is pushing that up, not forming a volcanic mountain, but a dome mountain, or maybe creating the force that made it fault block mountain. But most magma remains underground. As it does, sometimes it cools and solidifies to form intrusive, what kind of rock? They left off a word here. 3 types of rock. Igneous rock, because it's formed from molten lava, magma. Okay? Here are some of the features that magma can create. Now, they have the pictures here too, and they throw them all into one thing, and most of the time you won't see them this close together, but this is what it is. The first is called the batholith. Okay, batholith. Okay? When you see lith, think rocks. This is a suffix there, but it's rock. This is a huge intrusion of this magma that has forced its way up here, and these are the rocks that are left over from the batholith. These are probably igneous, intrusive igneous rocks. They formed underground, but now they've made their way to the surface. Okay? That's the batholith. Big, broad area that's pushed its way up. Okay? Large amount of crystallized magma. That's what this is. Okay? Now, you also have a stalk. That would be a smaller protrusion from a batholith. The batholith is down here. Here is the stalk. Okay? A smaller, not as big and major as the batholith. It's a small intrusion. Okay? It may have made its way to the surface or may have pushed something else up to the surface, but that's it. Okay? Now, where the batholith intrusions do reach the surface, now above them, were sedimentary rock. Horizontal layers of rock, but the batholith, when it forced it up, it bent. Remember, that was magma, so it bent the sedimentary rock, and the jagged parts where it bent here, that's called the hogback. I think of Arkansas Razorbacks, but this is the hogback, okay? This is sedimentary rock on the edge here, not igneous rock. But you see the edges of it, not the flat part, okay? So that would be your hogback, okay? Other processes, your dikes. Now, a stack is a sort of a big, broad, not as big as a batholith, but a small intrusion, but broad. A dike is where it finds a crack, and the magma forces up a fairly small area, and that's called the dike. It's pretty much a vertical, and here you'll have sedimentary rock here, but right in the middle you find a ridge of igneous rock. Intrusive igneous rock. That came from a dike. That's when it's vertical. When it's horizontal, like it finds a weakness between the layers and forces them there, that's called the sill. Here's a dike leading up to this sill, another dike leading to that sill. None of these have reached the surface. The only way you see it, if you were taking samples or something, taking a core down here, you see the various sedimentary rocks, and then suddenly you hit a really hard igneous rock and say, what are you doing here? Well, that was a sill. Then you hit more sedimentary rock underneath it. Okay? It acts like sedimentary rock, but it's not. It's igneous rock. Horizontal layer, that would be a sill. Okay? And then a litholith would be where a dike has come up, but then found a weakness between, a big weakness. These are weaknesses, but that's a pretty small, very confined to horizontal. Found a real weakness here, forced it up, sort of like another hogback here, okay? And that's called the litholith. Came out of not a batholith, a big broad area, but came out of a dike and forced a big broad area here that forced its way up. That's a litholith. Again, lith meaning rock. I don't know where they get batho and laco and that kind of stuff, but these are some of the other features that igneous rock, intrusive igneous rock, can form on a landscape. Okay? And this looks like maybe one of these over here and there too. But this is your batholith over here. The dike would be this little ridge here. Okay. And some of those things you won't see unless you drill down and count them. Okay. Before we get to overall picture, on page 497, which is where this figure is, figure 1924, the top of that is volcanoes change the world. Now, it sounds like a pretty overstatement, but not necessarily. They mention several really major volcanoes that have occurred over time. One was the eruption of Tambora in Indonesia, along that ring of fire, okay, Pacific Islands area, 1815 to 1816. That eruption was so massive, it blasted huge amounts of volcanic dust, ash, and gases high into the atmosphere. Most of the ashes and dust fell to earth around the volcano, but some dust particles and sulfur dioxide gas were pushed high into the atmosphere, and they found it halfway around the world, okay? In fact, in New England, in June of 1816, after the eruption was 1815 to 1816, around the end of the year, 7 months later, it snowed in New England. In June, okay, it was called, and the cold continued into July, crops failed, And 1816 became known as the year without summer, all because of that eruption halfway around the world, more than halfway around the world in Indonesia. Okay. They also mentioned 1982 eruption of El Chicon in Mexico, and how it affected the global temperatures a few tenths of a degree 2 or 3 years later. Okay. Now there is something mentioned here we're going to hit in a later chapter too, El Nino and La Nina. And I don't know if any of you are familiar with that. We'll hit that when we get to the weather chapter, but it's mentioned here if you wanted to look into that as a potential paper topic. Now in June 1991, a Philippine volcano, Mount Pinatubo, erupted, blasting twice as much gas and dust into the stratosphere as El Chicon had done a decade earlier, and that dust from Mount Pinatubo remained in the Earth's atmosphere for the next decade. 10 years that dust was still in the atmosphere. The haze from that caused some weather effects as well. So yeah, volcanoes can. Now, it's been probably 5 to 10 years ago. I was teaching this class, and one of my students was Filipino origin, and she knew Pinatubo and remembered either, I don't know if she was alive, but her parents or somebody, she knew of that eruption. She did her paper on Mount Pinatubo and really got learned a lot, I think, when she was doing her paper. So anyway, just wanted to mention that. All right. Yeah. Break? Yeah. Let's take about a 5-minute break. What is it, 3 o'clock now? Getting close? So yeah, we've been going quite a while. We're almost at the end. I'm going to, in fact, move the slide to overall picture, which will be, I don't know, they don't even have, oh yeah, there it is. Very last slide, I think it is. Well, no, one more side of it. So it's paused. No, it's not. Oops, turn on projector too. All right, any questions on anything that we've done so far? Okay. We're right at near the end of the chapter, so we'll be finishing up in just 1 or 2 slides, 2 or 3 slides maybe. Sorry, I didn't get this. Okay, the overall picture. All right. Mountain ranges are composites, not composite mountains, but composites of many different processes, each uniquely structured, okay? You'll have in a mountain range, you'll have folded mountains right next to faulted mountains, okay? You can have both of them, and possibly even volcanic activity, especially if you've had faulting going on, there could be volcanic activity going on there too. So it could be the mountain range could contain more than one of these. Most likely will, okay? And this is especially apparent along the converging of boundaries, plate boundaries. That's what it's talking about, where you have the subduction of the Pacific plate underneath, or the Nazca plate, either one, Nazca or the oh goodness, I think of the little strip plate up there. Set of islands by that same name, I can't remember it now. But anyway, where you have those kind of activities going on, where this Pacific plate is subducting underneath the North American plate, the continental crust, and somewhere way under there is probably where some of this volcanic activity is coming from. And that could be well inland of where you would expect. It's not right on the coast, okay? Now, Japan, that's right on the coast pretty much. Okay, this is especially apparent along the converging plate boundaries. Okay, and here's, there it is, one diffuser plate. I couldn't think of Juan de Fuca's name. Tiny little plate, probably the smallest plate out there. Pacific plate over here seems to be moving away from Juan de Fuca, but Juan de Fuca is going into the Pacific Northwest. Now this is Vancouver Island. Victoria is on Vancouver Island. There's the city of Vancouver is right here. This is Canada. Goodness, I can't think what province that is. I know it, but I can't think of the name of it. The last province in Canada. And here's Washington State here. Here's Idaho and Montana. Here's Oregon, more of Idaho. California, Nevada, Utah. This little bit right here is Wyoming, okay? And where Yellowstone is right here, okay? Mostly in Wyoming, but a little bit of it is in a bit of Montana, okay? That's where Yellowstone is. Now, if you'll notice here, Mount Garibaldi. I don't know much about it, but it's, I bet you, a volcanic mountain. Here's Mount Baker. I think it was a volcanic mountain. Glacier Peak is here. I don't know for sure. Here's Mount Rainier, definitely a volcanic mountain. Mount Adams, there's actually a series here they call the Presidential Mountains. There's Mount Adams here, Mount Jefferson down here somewhere. I just saw it, but I lost it now. There's Mount Jefferson. I think there's a couple others in there. There's Mount St. Helens here, just northern Oregon, southern Washington State, right near the boundary there. Here's Crater Lake. That's an extinct volcano, or at least we think it is now, and it's a really nicely formed crater there, filled pretty much with water. And I haven't seen it. Excuse me. But my nephew, when he was on his way to enter the Navy, he had gotten his commission and he was going to be stationed, his home port was going to be Hawaii, but he was on a ship that went out from Hawaii. And so he took a long time and took a great trip all through this area to see some of this sites, and he went to Crater Lake and was just amazed by it. Here's Mount Shasta. We've seen pictures of that. All these are volcanic mountains. Why? Because the Juan de Fuca plate is a oceanic plate subducting under the continental plate of the North American plate here, and where you can almost see where the activity is. Not right on the coast. It's inland because it's subducting under there, and that's where the friction occurs. Way under there, and that's where the volcanic activity comes all up and down there. Doesn't go much below that because Juan de Fuca ends right here. It's just a little bitty plate, okay? Sometimes I wonder if Vancouver Island isn't part of the plate and it's just separated there, but I don't know that for a fact. But anyway, that's it. Now the San Andreas Fault, I don't know where it actually begins, but it runs down pretty much like this. Pretty much hugging the coast here. It goes inland somewhere further down. Okay. Now, one of the most interesting features to me of this map here is this dark area. Okay? Can anyone tell what this dark area is? Here it says plateau basalts. What? What are basalts doing this far inland? How are basalts formed? The bottom of the ocean, where volcanic activity came up and you formed the quick cooling of the magma, and it became basaltic rock. Well, obviously, this was part of the ocean at one time, and things have changed. You know, plate tectonics has changed the whole features here. This has been uplifted as other things have shifted. Actually, what happened is the Atlantic, remember that ridge over here? It's been pushing the North American plate into the Pacific plate and the Juan de Fuca plate, and that's where the activity. So at one time, this was probably part of the Pacific. Okay, strange as it seems, because what is this thing right here? Salt Lake, the Great Salt Lake City, right around there. Guess what? It's salt because it was probably left over from the Pacific. Okay, it just is deep enough and very salty, by the way, saltier than the Pacific because it's evaporated a lot. Okay, amazing what's going on. And my wife and I drove a little bit through this and looked at some of these basalts, and it looked just like volcanic activity there, but no volcanoes anywhere in sight. This was underwater volcanic activity eons ago. Okay, and this is all more recent from the undercutting here. So it's amazing. If only the rocks could talk, they could they could fill us in on a lot of stuff we don't understand. That's it. The last slide. There was one guy featured here, James Hutton. Must have been hard of hearing too by his hearing horn that he's holding there. Scottish natural philosopher who pioneered, remember that word at the beginning? Uniformitarianism, geology. Nice little blurb on him. This blurb cannot be your source, but if you choose to write on him, you can get information from here. You have to find information outside the book, but the idea of writing on him is here. There was another guy mentioned here, Sir James Hall, and I think you can probably find some other things that you could write on there. Now, this chapter has one of the shortest, smallest summaries of any chapter, I think, in the book, okay? So there's not much here. Nothing, I say it every chapter, nothing replaces reading the chapter. Please read the chapter. Then go over the summary, and a lot of your keywords are in italics here, and you can go back and get the better definitions. The key terms are listed then after that with the page numbers where they were either first introduced or defined. Then applying the concepts. And while it's a short summary, we have 50 applying the concepts, multiple choice questions, great things to study for your test. Well, this test is a little different from many, but still a great thing to look at. Okay, questions for thought, 17 in this chapter. There were 16 in the last chapter. For further analysis, 4, that was the same as last chapter. The parallel exercises, we worked a few things like that on some of them, but you can look at those if you'd like. Okay. Now, we've got about 25 minutes before it's time to start the lab, so let's go on. Any questions on chapter 19? And like I said, I've said it before, let me say it again, make sure you heard it. We're going to do the lab, latitude and longitude lab. There was nothing in chapter 19 about latitude and longitude, but there's nothing in the lab manual that had anything to do with plate tectonics. So it's sort of hard to do that. So we're doing latitude and longitude to be our lab for this chapter. After that, when you turn that in or before you leave, be sure you pick up your take-home test. Because this chapter, the questions were just so bizarre, I chose just to make up, well, based on those questions, rewrite them so you could easily, I hope easily, find answers and do a take-home test. So let's, I guess my arrow was on that. There we go. So let's move on to chapter 20. All right. Set up for the slideshow from current slide. Whereas the last chapter was building the Earth's surface, this chapter is going to be shaping the Earth's surface. Because once it's been built, you start the process of wearing it away again. Okay? And we looked at that in the rock cycle. We're looking at it again here. Everything moves in cycles. Anyone have an idea where this might be? It looks a little like Grand Canyon. I don't know that it is, but you can see, notice the layers here. Probably what kind of rock? Sedimentary rock, okay? Been sedimented a long, long time. I'm guessing that's probably not the Grand Canyon, but the Grand Canyon looks a lot like this. I just don't see the river or anywhere for the river to be here, but it may be part of it. Let's see if that's the same as what I've got in our book here. Yeah, they don't even say where that is. Now, what has made that? Why do you have all these cuts through that sedimentary rock? Second? Erosion. Okay. Caused by what? Water predominantly. But there can be wind erosion, and we'll talk a little bit about gravity erosion. Gravity is involved with all of it except the wind. Okay? So that's what we're talking about largely in this chapter, is shaping the Earth's surface. The core concept, which is also here on page 505, the surface of the Earth is involved in, guess what, an ongoing process of destruction and tearing down of the higher elevations. So what was up here is going to be torn down. Later, it'll be built back up again. The process is continuous. Okay? In fact, it's not later, it's now too. Does anyone know where this is? What would you say the color of this rock is here? Yellowstone! That's exactly right. Now, I can't remember which this is. There's two of these incredible waterfalls. I mean, these are massive. These are tall trees here, by the way. Really tall trees. Okay? That gives you an idea how big that waterfall is. Okay? I think this is the upper Yellowstone Falls. I can't say for sure, but I believe it is. There's two of these, and the water is rushing down here, and later will drop again at the lower Yellowstone Falls. And then ultimately go into that lake, which is part of a crater of an enormous, enormous, enormous volcano. And this is, like you saw, corner of Wyoming and Montana. Way, way inland. No Pacific Rim there, you know, but still a massive volcano that happened there. But it could be that the ocean was much closer to them, so who knows. Because the salts weren't that far away. Okay. So we'll talk more about this when we get, and we'll see that picture again. So, you said erosion. Erosion is caused by something we call weathering. Okay? Not withering, but weathering. These are slow changes in the resulting in the breakup, crumbling, and other destructive activities of solid rock. Is that good, bad, or indifferent that rock is being broken up, crumbled, and otherwise destroyed? Good thing, bad thing, indifferent. What you think? Second? Indifferent. That's a good safe answer, isn't it? Yeah. It's kind of good. If the rock remained solid rock, we wouldn't be here because we wouldn't have anything to eat. Okay? So I'm glad the rock is being broken up. Okay? Breaking up, crumbling, otherwise destruction of solid rock. Slow changes, this is what we call weathering. So this isn't earthquake type stuff. This is slow changes. Now, three major types of weathering. Okay? Physical weathering, which on the next slide they'll call mechanical weathering. Same meaning. Physical weathering or mechanical weathering. Chemical weathering, and then biological weathering. Now, don't think that these three are completely isolated from one another. Sometimes they can be, but other times they work hand in glove with each other. Okay? Now, what do we mean by physical or mechanical? Well, we'll get to that. Just right now, those are the three types. Now, those three types of weathering or processes contribute to the rock cycle. How do they contribute to the rock cycle? Remember the rock cycle? That was chapters ago. We'd already been tested on that, so I don't need to remember it anymore, right? No!
No, I'm saying.
No, yeah, right. All right. How do they contribute to the rock cycle? What's one type of rock? Sedimentary. Where do those sediments come from? They came from the breakup, crumbling of other types of solid rock. Yeah, contributing to the rock cycle. Okay? And then, the most important, forming of soils. If y'all haven't taught it yet, my master's and my PhD were actually in botany, soil science. I did soil mineralogy and fertility for my master's and soil physics for my doctorate. So this is close to my heart. This is what we live on, folks. We work for soils. We're not here. Okay? The bookmark that I have in the book that I'm reading now says, soil sustain life. You know, that's so true. Okay. Formation of soils. Thank you very much. The movement of rock materials over the Earth's surface. Weathering contributes to that as well. But the downside is the erosion. So you're indifferent, good, bad, indifferent, bad. Most of the time, erosion is a very bad thing. The process of physically removing weathered materials from where they were and transporting them somewhere else. Erosion has two features to it, two components. The first is detachment, that's the removing, and then transport, that's moving it to other places. So that's what erosion is. Process of physically detaching and moving weathered materials. Not a good thing. Okay? Makes for some pretty landforms like the Grand Canyon, but then that's a lot of erosion that happens there. Okay. All right. The first of these, like I said, what's the other word for mechanical weathering? Physical weathering. The physical breakup of rocks without chemical change. Okay? So that would be like, now I'll use this example. We're going to see it later too. Some of the really pretty marble and maybe even granite or possibly limestone buildings, say downtown Birmingham or other places like that, they get sort of ugly looking after a while, you know, black stuff growing on them and just rather ugly. What do they do to come in and make them pretty again? Second? Pressure spraying, and what do they sometimes spray with? Sand. Sandblasting. Okay? That's a physical breakup without chemical change. Now, if they put in there, say, some acid or maybe Clorox or something like that, then there could be a little chemical change too. But if it's just sand or high pressure water, that's physical breakup without chemical change. You're just right. Now, that's people doing it. That's not natural. But the wind will pick up grains of sand and blow it against the mountain and slowly break up that solid rock on the mountain. Just in a slower sense, but that's sandblasting. Now, that's just one type. Physical breakup without chemical change. Here's a couple of others. One is wedging. That's not what you did to your younger brother. No, we're not talking about that. Okay, I can tell. Yeah, okay. What we mean by wedging, and by the way, if you haven't noticed this already, you probably will. Water is involved with most of this stuff, big time. So, let's just say that you had a tiny hairline crack in a otherwise solid rock, okay? And a little bit of moisture gets in there. Now what happens to water when it freezes? It expands. I want to say the only substance on the planet that when it gets colder, it expands other than contracts. And it expands. And it expands pretty big time too. Now why does it expand? Remember when we were talking about the crystal nature of solids and water, as light as its molecules are, 18 grams per mole, that's really lightweight. It should be a gas. But water is water, a liquid, because the hydrogen on this end and the oxygen on this end are polar. Plus side here, minus side there, and look, here we have Lexi. Okay. Has anyone else shown up that I didn't catch?
Mm-hmm.
Oh, who?
Me.
Oh, I'm sorry. Didn't see. Where's my glasses on? I need them. Or your glasses on? Okay. Edward. All right. So we're only missing Maurice, Cameron, Tegan, Chris, and Tamaya. Okay. That's right. Okay, so here's what we had. A little bit of moisture went into that tiny little hairline crack and then froze. When it froze, it expanded. Now, water can't break rock, can it? Freezing water, can it break rock? Have any of you ever had steel pipes freeze? Guess what? It can break those steel pipes. It can break rock. And it does break rock. So that's what wedging is. A little bit of water gets in there and then forces, when it freezes, that little bit of expansion is enough to break. Wedge that by frost. Now another thing can happen. We don't have that much frost down here, but boy, we have this. It says trees, but anything with roots. What's the really active part of a root? Does anyone know? Root hairs. Those tiny, tiny, tiny little roots you probably can't even see. You need a magnifying glass to see, oh, there's a little root hair. Now, why did I say that's a really active part of a root? That's where water gets absorbed, that's where nutrients get absorbed, and that's where plants' roots are a little bit tricky. Not only do they absorb things, they secrete things like acids. How do you think it gets the minerals it needs? It dissolves them with an acid secretion. Okay? And those tiny little root hairs grow into those tiny little crevices that were there because there's moisture in there, and they can secrete a little acid, dissolve some nutrient, and then they start sucking up that moisture in the nucleus. But guess what they do then? They grow. And they send out other little root hairs. And as they grow, they wedge the rock, okay, in those same tiny little hairline cracks. And that's exactly what they do. I think we'll see a picture maybe right now. Oh, that's not it. That's it. Look at those roots. Separated those rocks, separated these rocks, separated those rocks, wedged their way in, starting as a tiny little root hair, and then growing, and moving those rocks further and further apart. My wife's family had a place up on Smith Lake, and you can see this quite often in the sandstone around Smith Lake. This was some of the sandstone that I showed you a couple of labs ago were from. Those roots get right in there, break it apart. Okay? Now, this was the wedging done by water. Water gets down in there, but then when it freezes, pushes it apart, breaks it off. Okay? Now, this is sort of this is exfoliation. I was going to say, this is a different process here. I don't know even with glasses if I can read this stuff. Okay. I've mentioned Stone Mountain several times. There's a lot of things I don't like about Stone Mountain, but it's really what man has done to it. But Stone Mountain itself, have you ever been there? Okay, you have. Okay, what did you see all around the mountain?
Grass, just all.
I thought I saw an awful lot of gravel around the mountain.
Oh yeah, in the parking lot there was tons of gravel.
Yes, and you know why? Because whatever formed that, whatever pressure was underneath there, maybe that could be a batholith or something else growing there, pushing that granite up, pushing it up. Then when it reached the surface, it was being spread like this, and you got cracks in it. And that cracks could have had wedging in it. But the other thing is, because it was stretched like this, the surface was pulled apart. And it came off in pieces, that gravel. That's called, you ladies, do you ever exfoliate? Okay, you get off the outer layer. That's what's happening here naturally. It's exfoliating, and all around the base there, you'll see just pieces of gravel. Sometimes chunks of gravel, sometimes just little pieces that's all falling off the mountain. Okay? Reduced pressure effect, because underneath you got a lot of pressure. Up here, it's being spread out, less pressure, and it cracks. It falls off. Fractures caused by expansion of the underlying rock, and that's exfoliation. Two types of physical breakup. Wedging, either by water or by roots. See, this is biological as well as physical. The trees are biological. The water, that's physical. Okay? But the trees were also chemical. Remember, they secreted acid. So you see, it's all a mix of all three of them. Okay? And then exfoliation was another type of physical or mechanical weathering. Okay? How many times have you tripped on one of those where that tree root is actually, we got a big old white oak. It would take two of us maybe to get our arms around the tree and touch fingers maybe right by our driveway. I wouldn't have put a driveway there, I don't think, but they did. And boy, that dropped. Big old chunk of concrete is up like this. And trees don't let things get in the way too much. That would be a form of wedging. That's not natural rock, but that's the same principle. Okay? Oh, I forgot to look at the text. One of the prettiest pictures is figure 20.1. Way too early. This is Utah's Rainbow Bridge National Monument, example of a landform created by the sculpting power of moving water. But quite often, these kind of forms could have been also moving wind as well, wind carrying chunks of rock like sandblasting. Okay. Figure 20.2 is sort of what I was describing around Stone Mountain, but not to this degree. The piles of rocks and rock fragments around the mass of rock, evidence that the solid rock is slowly crumbling away. This is Chiricahua Mountains in Arizona. I've never been there, but it looks like a beautiful place to visit. Okay. A little gal walking down a road, but you can see cracks where the trees have forced it up. And growing trees break, separate, move, large solid rocks. So just more and more of that. Now, I think that's probably what should have been in these other, this empty space here, some of these great figures from your text. But let's move on. I haven't really done great justice to mechanical weathering. We'll do more later. We'll talk about some more later. But then they get to chemical weathering. Now, again, these don't work independently of each other. They work hand in glove with each other. What we mean by chemical weathering is decomposition of minerals by chemical reaction, as opposed to strictly physical reactions. Now, your physical reactions are grinding, moving, splitting, that kind of stuff. Chemical reactions, they list 3 here, and in a sense, water is involved with all 3. A little bit less so in oxidation, but still is involved in that. The first of these is oxidation, and I hope that the name implies to you what it is. Something oxidizes or changes its chemical structure. Oxygen is a very, very, very reactive gas, and when it gets in contact with something else, it tends to react with it. And oxidation is one of these. It's reactions with oxygen, and the thing that this is focusing on is iron. And if you think about it, iron was the most predominant element in the whole Earth. Not in the surface, not on the crust, but in the whole Earth, it was number 1, if I'm not mistaken. Okay? But there's plenty of iron on the surface, and iron is usually hard, dark, rich, heavy, hangs together really well. Get it in touch with oxygen, it oxidizes. What's another term we use for that? Rust. And when it's rusted, is it hard, strong, durable? No, it can break easily. So oxidation is a chemical reaction. It happens with iron, but it happens with most of the other metals as well. They will oxidize. Okay, the iron becomes the red oxides. Now, is that occurring anywhere in this room? Oh, what's going on here? Yes. What do we have in our blood? Yeah, we call it hemoglobin. Hemoglobin is a claw-like molecule that has a single ion or atom inside the claw. Okay? And that hemoglobin is in your blood, and it travels around your body. And when it goes to your lungs, this blue blood that you see in your veins here gets oxidized by your lungs. The oxygen gets in touch and becomes arterial blood, which is red. Okay? Because if you don't do it, but if you were to accidentally cut or nick a vein, if you look at it immediately, it might look blue when it comes up, but immediately it turns red because it gets exposed to oxygen in the air. Well, that happens in your lungs because the iron that's in the hemoglobin, when it's blue, it's FeO, ferrous iron. And then it oxidizes further when it gets in your lungs and becomes ferric oxide, Fe2O3. And that ferric oxide then in your arteries, you don't see your arteries on the surface because those are the oxygen carrying, they're deep, okay? And those arteries are carrying that oxygen to the various parts of your body where you need it, and that's where giving the oxygen to the muscle, the tissue, the tongues, the ears, the brain, whatever is needing to use that energy that it gets from oxidizing, and then it takes the oxygen away, it becomes ferrous again, and returns as blue blood. Okay, your venal blood. Okay, so that's going on right inside of us. Okay, it goes on everywhere. Oxygen combines with stuff, especially with iron. There's a hill, it's now my sister's part of the farm, and that hill was a red clay hill. I mean, We used to farm it, but pretty dissected, but it's red clay hill. I mean, typical red clay, Georgia red clay, But then at the base of the hill, it was great, down there, and it moves into a swamp. I thought, well, all the sand and everything else washed off the hill and it's down there at the bottom, so that's it. And then I found out, no, that isn't. That's clay down there too. It's the same clay, except up here it's well drained, so it's ferric oxide, Fe2O3, but down there where it's swampy, wet, it doesn't oxidize as easily, and it's ferrous, blue soil. Okay. Same things happening on the hillside, happening in your veins. Okay, reactions with oxygen, that's oxidation. So, marginally water is involved, how so? Where does metals rust the worst? In the presence of moisture. Exactly. Okay. Water acts as a catalyst. It's not part of the reaction itself, but it encourages the reaction to happen. It's a catalyst. Okay? How are we doing on time? Oh! Isn't it time? Past time. Sorry about that. You want to start with this slide again? It was so much fun the first time. Y'all can remember where we left off, can't you? I'm sorry, I got carried away. But not far enough, you say. No! You didn't say that. Okay. See if I can find where we are here. Okay, do you think we beat oxidation to death? Yes. Okay, we'll pick up with carbonation next. Okay. All right, so we'll end the slideshow. All right. All right. So read the lab. What's another name for the parallels? Say again? Those are also called the longitude lines. Okay? And latitude lines. Okay? And the parallels, the ones that go this way, that's what you use to measure your latitude.
Wait. I thought you said parallels were longitude.
I know I said it wrong. Latitude. I'm sorry.
Okay, latitude is parallels?
Yeah, the parallels are the latitude lines. And the longitude are the ones that go north to south. The parallels parallel the equator. And the longitude lines go north to south between. Every one of them goes through the north and south pole. Every one. And those are another name for the longitude lines are the meridians. Okay? What is the number one meridian? Near London, that's called the prime meridian, and it's actually 0. It's not number 1, but it's 0, and it is. Second. Yeah, the Greenwich, England. Yeah, Greenwich, England is the Royal Naval Observatory in Greenwich. Yeah, they say Greenwich Observatory. The Royal Naval Observatory. All right, now we're not going to mess around with soft clay, protractors, toothpicks, so you can picture this, and that's what reading the next topic is going to be about. Just imagine you have clay, get it all over your fingers, cut it in there, put the protractor in, and measure it. So you be reading that while I set up the rest of the lab. Okay? And once you've read all those, then I think you can answer the questions of the results. What information does the latitude and the location tell you? What information does the longitude tell you? And then, according to a map or a globe, what is the approximate latitude and longitude of the place where you live? And what I'll do is bring in an Alabama atlas and gazetteer, whatever that is. And most of you, I think, will find that you live on pages 30 and 31. Okay? You may not have realized that, but that's where you live. Some of you may be a page or two over, I don't know. I bet you most of you live on pages 31 and 32. The horizontal lines that you see here, and most of the time they will have, these are the latitude lines. You can find the latitude over here on the side. It's either given in degrees, minutes, and seconds, sometimes to the 10th of a second, or it's given in fractions of a degree. So whichever you want to do, okay? The longitude lines are measured, those are the vertical lines here, and those are also given at the top and bottom of the page in degrees, minutes, and seconds, or decimal degrees. So either one, so once you have answered the first two, then you can use this and find where you live and what your closest latitude, longitude lines are. You can pick the intersection of the square closest to where you live. Okay? And I think I see what happened here. If you look at your lab, I see a page 339, a 340, a 340, a 341, a 342, a 342. I don't know how this happened. And then a 343.
Mine's right.
So about,
Mine's right.
okay, some of them are right and some of them may not be. That may be why she recopied and then put them in my box. What's that? Yeah. So if yours are okay, you're fine. If not, just X through the second page of a duplicate. Okay? But anyway, page 342, you can answer those three questions. You don't have to answer but one set. And then at the top of 343, explain how minutes and seconds are used to identify a location more precisely. That's all in the reading. Okay? So while y'all are doing that, I will set up the next part of the lab. Okay? It's going to take me a minute. I've got to run down to the library. I meant to do this beforehand. But I'll also tell you part of the rest of it. Here we have a cup named Africa. Here we have a cup named Alabama. Here we have a cup named Asia. Here we have a cup named Australia. Here we have a cup named Canada. Here we have a cup named Europe. Here we have a cup named South America, and then one named United States. Okay? Now, in these cups are strips of paper with names of cities on them. Okay? Now, don't mess with these yet. But what I'm going to do, if you wanted to start messing with them, you can. Take the Alabama cup and find a city, and don't be picky, just whichever one you choose, pick it up, then go through here. Now, you can use the chart at the back of this, and it gives the page numbers, like 31 and 30 and 31 that we were looking at. There's Birmingham in the middle, Bessemer down here. That's the one we were looking at. So find the city, or as close to the city as you can, get the page number, go to the page number, and record its latitude and longitude. You're only going to need one city beside your hometown, one city from this cup, and you can be doing that. Okay? Now, while I'm going to, in addition to answering the question, here is a U.S. road atlas, okay? And you can find every state in the Union, and in the state, every city in that state on these, and that's where you'll choose one and only one from the U.S. cup, okay? So find the city from the U.S. and look it up. In this one, find its latitude and longitude. This one you can get to the nearest second. This one, depending on the size of the state, this is Missouri. This is, here's East Texas, okay? Here you can only read to you have to look around for them. I don't even see it on this one. Ah, here it is. Okay. It's hard to see. On the edges of where the states are, you can see just inside that, like this is 32 degrees 00 minutes. The next one that lists up here is 34 degrees, no, 33. So this you can only get to the nearest degree on Texas. Now maybe some of the others you can get more. So one Alabama, one U.S. using these. Okay? I'm going to go get the other atlases from the library and I'll bring them right up. So be answering your questions. You can work in groups, okay, and answer your questions and use those. Yeah, you might need another piece of paper to write on, yes. Yeah, and let's put this on pause. Yeah, thank you. Okay.
So you wouldn't have 10 minutes of this.
I guess I can turn this off. Could I get you to flip up the other light? On right near the door. Now everybody's in the light. Okay. Here are 3 atlases to find the rest of the world shots. Okay? I don't know where to put them. Okay. I'm going to put one on this desk, on this desk, and one on the desk over here. Okay. So that's where you, okay. So here's the rest of the lab. Okay. Kind of broke up in the middle of that. Okay. So, going back over this, you have 5 questions here under results. 1, 2, 3, 4, 5. Okay? That's all, folks. We need 20 more points for your thing. So, now I have more white pages on this than you do, but if you want to write on the back, is your back clean? Yeah, if you want to do that, you're going to pick 10 cities. 1 from Alabama, 1 from the U.S. Okay? 8 more cities. Okay? 1 from Australia. Okay? 1 from Canada. Okay? 6 more cities. 1 from South America. Okay? 10 cities. Did I say it right? 1 from Alabama, 1 from the U.S., 1 from Australia, 1 from Canada, and 1 from South America, and 1 from, okay, not yet. Yeah. So that's 5 cities. Okay. Yeah, that's it. Okay. Now, got 3 continents left. Okay? Europe, Asia, and Africa. You pick any 2 of those and pick 2 cities from those 2, 1 city from the remaining. That's how you get your last 5. Most populous, the ones with the most cities in them, are Europe, Asia, and Africa. Pick 2 from 2 of those and 1 from the other. And those will be your other 5 cities. Okay? And you record, going to your big atlases, your latitude and longitudes for each of those cities, each place. The Alabama, okay, your hometown, that's question number 3, you get from here. The Alabama one, you get from one of the other pages in here. Okay? The U.S., you'll get from here, and then all the rest of them you get from one of those 3 atlases. Does that make sense? So on the back, list 10 cities. Okay? What I would do if I were you is come up and draw your city, write the name, put it back. Draw the city, write its name. Draw Well, 2 cities, right? Whatever. Get 10 cities here, and then have a column for latitude, have a column for longitude. Okay? And that's 1 from the U.S., 1 from Alabama, besides the one you already did on question 3 for Alabama. And then 1 from Canada, 1 from Australia, 1 from South America. And then 2 from 2 of the 3 big ones, and 1 from the other 3. The other 30. Okay. Any questions on that? Okay. I'm going to run down. How many others needed? Okay. We just had cities falling all over the floor. Okay. Now, if you find one you can't read, which could happen because I wrote them, or if you find one that you don't know where it's from, or perhaps it's in the wrong cup, and that happens because cups get spilled. Okay? So ask me and I'll read it to you and say, no, that belongs in this one. Okay? So any questions before I get going? So how many needed faces in the moon lab? I knew of 2 people. Only 2? Faces of the moon. You didn't get a face of the moon lab, or you have a question?
No, I thought you asked a question.
Oh, no. How many else? Just 2? So I've got to go make copies of these for those, and I'll be back very shortly. Okay?
Yeah.
I just recalled that I forgot to say something that's probably pretty important, so let me get my... Oh, I forgot to turn it back off again. Okay. Let me say this. Every latitude you write down, remember you can either write it in degrees, minutes, and seconds, but it has to be followed by a letter. What letters? Latitude. N or S, north or south. What does that mean? North of the equator or south of the equator. Every longitude that you write down, including your hometown, by the way, you need to follow by a letter too. What would those be? Say again? Not north. East or west. Okay, now what would be east? Anything east of the prime meridian, back down all the way around to the international date line, or west would be anything west of the prime meridian all the way around to the international date line. So every latitude has to have to be followed either by an N or an S, every longitude by an E or a W. Okay? So don't forget to put those in. Okay, I'm going to put it on